Hello, data science students. I hope you're all doing well, staying happy, healthy, and safe. Today we're going to continue our discussion of linear regression. So last time we talked about what linear regression was, why it's important, and in particular for the human, why it involves a good bit of imagination. So we can look at a set of data and see trends and see patterns in it. But as data scientists and statisticians, we can't trust the human intuition too much. We want to quantify it. We can be guided by those things, but we have to mathematically and numerically show evidence for what we see in our data. So we began our discussion, or rather we concluded our discussion last time by looking at this. We talked about how we usually represent lines using a slope-intercept equation. Now, if you look at this typical slope-intercept equation, it looks very, very similar to a 1-degree polynomial model. That's because it effectively is a 1-degree polynomial model. So in order for us to make a model of a set of data, a linear model anyway, there's certain information we have to understand, we have to get from our data. One is going to be our slope, the other one is going to be our y-intercept. If we can find those things, we can make a linear equation that represents the data that we're looking at. Now, how are we going to do that? Well, like anybody, you've got certain tools already at your disposal. So if we can use some tools that we already have to do something more complicated, like generating a linear model, we want to do that. So let's look at some of the tools that we already have in our toolbox. So some of the tools that we've been using our averages, like our mean, our mode, our median, things like our variance, covariance, correlation, standard deviation. And remember, these things can be separated effectively into two different categories. The first category are our averages. Think of this as the top tray in your toolbox of statistical tools. Our averages typically describe the centerness of our distributions. So thinking back to our normal distributions, we have a bell curve, and the average typically represents the center, where the peak of that bell curve is going to be. Now, looking at our standard deviation and our correlation and variance and those kind of things, these things describe change, patterns of change, and spread within our data. So think of this as that second tray inside of our toolbox. So between these two trays in our toolbox, we have enough tools to do something more complicated and build one of these linear regression models. So let's start by talking about our slope. What is slope? Slope is the change on a line along the y direction divided by the change along the x direction. So effectively, it's the distance between the bottom of your data on your y-axis to the top of your data on your y-axis divided by the bottom of your x values along your x-axis to the top of your x values along your x-axis. And so that distance, that change there is, well, a distance. One of these that we've talked about, we said earlier in class that the formula for one of these guys looks a lot like the distance equation. And you can kind of think of it as the distance around a mean in your data set. Which one of those was that? If I was in person, you guys could tell me. It's standard deviation, Dr. Jones. I can hear you all out there in cyberspace. You're right, standard deviation. So we can sort of think of standard deviation as being the distance our data travels around our mean. So what we can do is we can utilize our standard deviation to get the change in the spread of our values along the y-axis and the spread of our values along the x-axis. So we can say our slope equals our standard deviation along the y-axis divided by our standard deviation along the x-axis. And that gets us really close. But now remember something. Standard deviations are always positive. Slopes can be positive or negative. So a positive slope will go in this direction, a negative slope will go in this direction. And, our data can move one way or the other. It can have a negative slope, it can have a positive slope. So how do we incorporate a sign into this using our current statistical tools? Well, one way for us to do that is to utilize our That's what I already said. Utilize, there we go, our correlation. So remember, correlation gives us a value in between -1 and +1 that relates how well correlated changes along our x-axis are to changes along our y-axis. And so if something has a very strong correlation, it's going to be very close to positive or -1. If things have a positive correlation, they're moving in concert with each other. As x increases, y increases as well. Conversely, if things have a negative correlation, as y or x increases, the other axis decreases. And so we can use this to get the sign out of the change in our data, so the direction of that change. So we can approximate the slope within our data using our correlation of x to y multiplied by the ratio of our standard deviation y over our standard deviation x. And so this gives us a very good approximation of what the slope in our data should be. So we have our slope. Now we need to focus on finding our y-intercept. Now remember, our y-intercept is the point along our y-axis where x is going to equal 0. So in other words, it's going to be the place along our y-axis where our line crosses it. Now how are we going to figure that out? Well, it's not as difficult as you might think. So if we move on, let's see. We can solve this actually just using good old algebra. So let's take a look at our slope-intercept equation for a second. So y equals mx plus b. So if we do a little bit of moving around of our variables, we take mx and move that to the same side as y, we get b on one side by itself. So now we have b, which is our y-intercept, equal to y minus m times x. Beautiful! We've solved the problem, right? Except x and y, what are those guys supposed to be? Those represent an xy point that we already know along our line. And we don't know any points along our line. We just have these scattering of points around our line that we're trying to model. So how do we figure this out? Well, we've got to use some of our statistical tools again. So let's say hypothetically we're trying to model this line right here. And we know that the model of our line runs through the middle of this data, but we don't necessarily know a point that's going to be on that line. But can we approximate a point that's going to be on that line? Now I said a really important word. I said middle of the data. So if we think about the middle of our data, we've used middle or center to describe something already. And the thing we've tried to describe, or used that word to describe, has been our averages. So can we approximate the point that's in the middle of all this that's going to be very, very close and perhaps even on the line that we're trying to generate? And we can approximate it. We can approximate the center of our data set. And of course, we already said this earlier, our averages are ways of describing the center of our data set. So if we can get the average of all of our x values and the average of all of our y values, that's going to give us a point that's on average in the middle of our data set and on average close to the center of our line. So we can now replace y in our equation with the mean of our y values and x in our equation by the mean of our x values. So our approximate y-intercept is now equal to the mean of y minus our slope, our approximated slope, multiplied by the mean of our x values. And so this is going to give us a very, very close approximation of the y-intercept for our linear model. And now that we combine all these things together, we can now use that to come up with a rough equation. Actually, not just a rough equation, usually a fairly good equation as long as your data follows linear trends for modeling the patterns within our data set. Now, Numpy that we've used in class quite a bit has a standard deviation, a mean function, and a correlation function built into it. And now these guys mostly function the way that you would expect. So if you give the standard deviation function a list of values, it's going to give you a single number out that's going to be your standard deviation. Similarly, you get your mean, numpy.mean, you give it a list of values, it'll give you a single number out that's going to be the mean of that list. Numpy core coef, that stands for correlation coefficient. This, you give it a list of your x values, a list of your y values, and you would expect it to give you a correlation number out the other side. And it does, but just not in the way that you expect. Now keep in mind, NumPy is designed to do a lot of really cool and complicated math. So you can actually use this correlation coefficient function to get correlations for many, many sets of data, not just two, not just an X list and a Y list. So what it actually gives you out is a correlation matrix. Let's see, we get the next slide. There we go. So you get something out that looks like this. So what it's going to give you is actually a matrix representing the correlations between each list of values that you give it. So in our case, we're going to give it an X list and a Y list. So our X values and our Y values. Now, the diagonals along this matrix are always going to be 1. Why? Because look at what you're correlating. You're correlating X to X and Y to Y along the diagonal. So what is the correlation of something with itself? It's always going to be 1 to 1. So the values along the diagonal, not going to be of much use to you. But the values on either side of the diagonal, those are going to be useful. So the values here and values here are the ones that you're actually going to want to use for your correlation coefficient when calculating your slopes. Now, these values are going to be symmetric on either side of the diagonals, because what we have is we've got the correlation of y to x here, and we've got the correlation of x to y here. It's the same correlation. So it's going to be mirrored along the diagonal. And so you can see this more clearly when you start doing correlations of more than one axis. And you can see, that you've got correlation of x to y, y to z, so on and so forth. And those values get mirrored along that diagonal. But for our purposes, for your linear regression project, you're just going to have something that looks like this. So you can reference either your correlation coefficient matrix that comes out index 0, 1 or 1, 0. Either one of those is going to give you the correlation coefficient for your x to y correlations. And this is the value that you're going to need to use when calculating your slope for your projects. Okay, so we're going to wrap it up there. If you have any questions, please feel free to let me know. I'm going to be holding virtual office hours, again, weekdays, unless otherwise noted, from 4 to 5 p.m. I'll do others by appointment. If you need to get in touch with me and you want to Skype and have a person-to-person, in-person, face-to-face, that's what I'm looking for. A face-to-face talk. We'll set that up. Otherwise, you're more than welcome to hop into my virtual office hours. If you go to either my personal website or the lab website, there's a giant blue button that says Skype office hours. If you click it, you come to another page where you enter your email address. Enter your email address, click submit, and you'll get forwarded directly to me on Skype. And that way we can talk. Keep in mind, it is advising and registration time. If you have not seen your advisor to get your advising holds lifted, do that immediately. I know I've still got a lot of students who haven't come to see me yet. Some of you are watching. So if you're one of my advisees and you haven't come to see me for advising, get in touch with me. I've actually made a lot of this online through the website, so it's actually kind of easier than coming to see me in person and filling out all that paperwork. A little more clicking, a little more typing, and you're just kind of done. So if you guys can do that, do it as soon as you can. And otherwise, I'll see you all in cyberspace. Bye-bye.